So in 7.3, they focus their attention on optimizing functions with several variables. Primarily, it's going to be situations involving two variables, although they do give some examples where there may be three variables involved, and even offer some examples for you to work on where there's three variables involved. But this course doesn't really assign those to you necessarily. Um, but let's have a look and kind of review a couple of things before we get started into this. From the previous lesson, we talked about relative maximums, minimums, and even saddle points. All three of these are going to come up when I eventually do tests in this particular lesson for critical points. Relative maximums and relative minimums are actual critical points. Saddle points will show up as a critical point, and I'll actually have to determine whether or not that is the case using some of the testing that we do in this particular lesson. So we're going to see how to maximize and minimize such functions by finding critical points and using a two-variable version of the second derivative test. They're going into talking about the applications and things like that. But as I say, it can work with more variables than that. It just gets much more complicated to do so. So keep that in mind as we go through that. But essentially, what we look to do is a critical point, AB, is a circumstance where both the partial derivative with respect to x and the partial derivative with respect to y at a given ordered pairs are both set equal to 0. So what I do to find critical points is I essentially find the values that make that indeed happen. So, an example. I want to find all the critical points of this function here. So what I first do is I find the partial derivative with respect to x and the partial derivative with respect to y. And here they are. And what we do is we set these equal to 0. And we solve for them. And what we end up getting is a system of equations. Now, you learned ways of solving systems of equations in previous courses. Since you won't have a calculator handy, using matrices may not be the best way of doing so. The two methods we tend to focus a lot of our attention on are either using elimination or substitution. A lot of the work that they seem to show seems to go towards elimination. So if I have these two equations that equal to 0, if I basically the whole premise behind the elimination model of the solving system of equations is that it uses the principle that I can multiply any equation on both sides by the same number, and I'd keep the equation still basically the same. And if I add two equations together that have a solution for x and y, then I would get yet a third equation that would have the same solution for x and y. And so what we tend to do for elimination is that I pick a variable, x or y, for which I'm going to choose to eliminate. So as you see, back to the original equation, what we actually did in this situation here is I multiplied this bottom equation, the entire thing, both sides, by -2. And what that does is it gives me the equation on the bottom, -6x minus 4y minus 2 equals 0. And when I add the two equations together, all that basically happens is that this gets canceled. I'm left with a third equation now that only has one variable in it. So I could say that, -y equals -1 or y equals 1 would be a solution. And then I could go back and figure out what x is. So x would equal -1 as a result. So basically, I'm looking for an xy pairing that's going to make both equations equal to 0 at the same time. Now, this is a potential critical point. It's still potential at this point because we don't really consider a saddle point a critical point. So negative 1, 1 is the coordinates for a potential critical point. The thing is, I don't know what it is yet. You know, I don't know if it's a maximum, a minimum, or a saddle point, which at that point I would say it's really not. Well, take that back. Critical point, yes. Extreme point, no. I mean, in one variable, they're the same thing. In multiple variables, critical points and extreme points are not necessarily the same thing. So, so the first thing we have to do is find a critical point. So, after looking at this example, let's have you have a turn. I want you to find the critical point or critical points of this equation here. Well, as we did in the previous one, I'm going to find two partial derivatives. I'm going to first figure out what the partial derivative with respect to x is, and I'm going to figure out what the partial derivative with respect to y is. So as far as the one for x, I'm going to treat all the y's as constants. So when I take the derivative of 2xy, I just get 2y. The minus 2x squared, well, minus 2x squared is going to give me a minus 4x. The minus 3y squared, that's considered a constant. So if I take the derivative of that constant, it's going to be 0, so I ignore that. The next one, the 4x, the derivative of that with respect to x would be a plus 4. The minus 12y and the plus 5 are both considered constants in this case, so they would both become zeros. And so this would be my partial derivative with respect to x. When I do the partial derivative with respect to y, I end up with 2y. The minus 2x squared is a constant, so it's going to become 0. The minus 3y squared, I take its derivative, I get minus 6y. And I don't know why I put an x in that first one, because it's the y that's treated as a variable. It's the x that's the constant that stays. So, the 4x will be a constant. The minus 12y, its derivative would be minus 12. And the plus 5 is a constant, so its derivative would equal 0 as well. So now I said both of these equal to 0. Although I might want to rearrange it. I mean, the first one, I have negative 4x plus 2y plus 4 equals 0. 2x minus 6y minus 12 equals 0. And if I look at this, you know, I'm going to choose to eliminate the x's, because if I just simply multiply the bottom equation by 2, both sides, I'm going to get a positive 4x, and then when I eventually add the two equations together, I'll have a negative 4x plus 4x. They'll cancel. So what I end up with for my system is negative 4x plus 2y plus 4 equals 0. 4x minus 12y minus 24 equals 0. When I add, these cancel. I end up with a negative 10y minus 20 equaling 0, which means I have negative 10y equaling 20. Divide both sides by negative 10, I get y equals negative 2. And so I could go back to any one of these first equations, one of these two, and plug in the negative 2. I'm going to use the f of x value. 2 times negative 2 minus 4x plus 4 equals 0. So negative 4 minus 4x plus 4 equals 0. The minus 4 here and the plus 4 here would just cancel. Negative 4x equaling 0 means that x has to equal 0. So I get one critical point at 0, negative 2. I don't know what that critical point is, It could be a maximum, it could be a minimum, or it could be a saddle point, which means it's neither. So that's what we have to get into next, is how do we tell, once we get a critical point, what kind it is. To determine whether f of xy has a relative maximum, a relative minimum, or a saddle point at a critical point, we use the following D test, which is a generalization of the second derivative test. And so this is the main formula we're looking at. We do the product of f sub xx times f sub yy minus f sub xy squared. Now the whole idea behind this is for mostly polynomial situations, this and yx, f sub yx are the same thing. So you're kind of looking at it as from a perspective that you're doing f sub xy times f sub yx. That's why they made note of it before, but remember, not all functions do that. This is the formula they're using for our purposes, but I've seen other books state instead of this, it's f sub xx times f sub yy minus f sub xy times f sub yx. But for the circumstance that we're dealing in this book, this formula will suffice. So now, the two things we pay attention to as we do this particular rule is the value of f sub xx and, of course, d. I have a maximum if d is greater than 0 and f sub xx is less than 0. I have a relative minimum if d is greater than 0 and f sub xx is greater than 0. And I have a saddle point if this d value is less than 0. A lot of sometimes I get asked the question, what happens when d equals 0? That's more of a complicated answer than we need to kind of go into at this point, because it's kind of the two variable version at that point of what would kind of be an inflection point, but we don't have what's called concavity, so to speak, although we do have kind of a cupping out upward and inward and stuff like that. So but that's what happens if d equals 0. You have one of those circumstances. It's still not going to be a maximum or a minimum, so we would exclude those anyway. So let's find the relative extreme values of f of xy being this function, if it actually does exist. I mean, if I find out it's a saddle point, it doesn't exist. So so I give it this function here. Now it says we find critical points by setting the two partials equal to 0 and solving. Okay, this is what we did in example 1. So go back to example 1, and we did find one critical point at negative 1, 1. So now what we're going to do is say, okay, well, what is this critical point? Well, I do the fxx. Now we have already found out that fx was this here. So I take the derivative of that with respect to x again. I just get 6. The 3y and the 3 are counted as constants. They become zeros, and I differentiate. fxy, I now take that same thing, and I take the derivative with respect to y. Well, I do fyy next. This is the list they do it. I would probably go right to this one next. If I take that derivative of fx with respect to y now, the 6x and the 3 are constants. The derivative of the 3y is just 3. And fyy, I would just get 2 because this and this are constant again. So some of the cases that we're going to be getting here, we're not going to get a function of x, we're just going to get a number. So I mean, even though I'm supposed to plug in the negative 1, 1, there's nothing to plug into. So there's nothing for me to do the substitution. I mean, fxx for negative 1, 1, or any other ordered pair for that matter is going to be the exact same. It's going to be 6. So, but if I apply the formula for d, 6 times 2 minus 3 squared, I get 3. So d is positive. It's more than 0. So I do have a critical point. I now have to look at fxx, which is also positive. So that means that we have a relative minimum here. So that's how we figure it out. now what they're doing is oftentimes you'll be asked to figure out what is the minimum value at that point. Okay, and that's going to be a question they're going to ask you too. I mean, because f negative 1, me getting a value for that is what's going to give me what the minimum value is. So plug all those numbers in. I end up getting 5. So this function with two variables is going to have a minimum value of 5 when x equals negative 1 and y equals 1. So now it's your turn for this. I want you to find and I'm going to have you do more of the work this time because I'm not giving you the same function you had in the first your turn. So you're going to get a function that's a little different here, and I'm going to ask you to break it down. Okay. The first thing I'm going to ask you to do is tell me what fx is. Well, that means I'm doing the partial derivative with respect to x, so I'm going to have 3x squared. The y squared becomes 0 because that's a constant, minus 3. And the 6y treated again as a constant, so it's going to become 0. Now I'm going to ask you to find the derivative, the partial derivative with respect to y. So the partial derivative with respect to y is I'm going to have the x cubed is going to be acting as a constant in that case, so I'm going to have nothing for that. The minus y squared, its derivative is going to be a negative 2y. The minus 3x is a constant, so that's going to become another 0. And the plus 6y, its derivative is going to be a plus 6. Now for this case here, it's a little easier. I don't have to do a system because I actually have two equations that only have one variable in it. So in this case here, 3x squared minus 3 equals 0, which means that 3x squared equals 3, which means x squared equals 1, which means x is going to equal a plus or minus 1. And this one here, negative 2y plus 6 equals 0, means that negative 2y is going to equal negative 6, which means y is going to be 3. So, tell me now with this information, what are the critical points for this function? Well, it's pretty straightforward. I mean, the y has to be 3, x could be 1 or negative 1, so 1, 3 is one potential critical point, or is a critical point. Negative 1, 3 is the other. So these are my critical points. Now what I have to do is figure out what kind of values are these. Are they minimums, maximums, or saddle points? So now, I mean, I have fx, I have fy. I got to figure out what fxx is, fxy is, and fyy is. So fxx is just going to be 6x. fxy is going to be 0 because when I go to f sub x, I don't have any y's left in there. As a result, the 3x squared minus 3 is all one big constant, so I take the derivative of a constant, I get 0. fyy means I go to the fy function, derivative of that's going to be negative 2. So when I look at these two critical points, I'm going to go to a different color. At 1, 3, my d value is going to be fxx evaluated at 1, 3. So I'm going to have 6 times the x value 1 times fyy at 1, 3, which is just going to be negative 2. And I'm going to subtract fxy squared, which is 0 squared, and I get negative 12, which is less than 0. So that means at 1, 3, I have a saddle point. At negative 1, 3, I get the d value to be 6 times negative 1 times negative 2 minus 0 squared, which gives me a positive 12, which is greater than 0. Along with that, fxx at negative 1, 3 is 6 times negative 1, which is negative 6, which is less than 0. That means I have a relative maximum at negative 1, 3. And the maximum value is going to be f of negative 1, 3, which would be negative 1 minus 9 minus 3 times negative 1 plus 18. So I have negative 10 plus 21, which gives me an 11. So the maximum value of the function is 11. That occurs when my ordered pair is negative 1, 3. So it's a relative maximum. And at 1, 3, I have a saddle point. Now they go into some application problems like maximizing profit and things of that nature, and what it means to flood the market and all that good stuff. Good for you to read. Suppose that a company produces two products, A and B, and that the two price functions are P of X and Q of Y. Sometimes they'll say, like, P sub A. I've seen them write it this way sometimes, and then sometimes you'll see me write it this way. P sub B. I'm still using it in terms of X and Y, because they're usually two different products and I'm counting different units. So the cost function, will oftentimes be a given function. So if I want to figure out the profit, I'm just going to take the price function times the number of units for product A, do the same thing for product B, add those together, subtract away the cost function. That's going to give me a profit. So for an example, Universal Motors makes compact and mid-sized cars. The price function for compacts is P equals 17 minus 2x for x values between 0 and 8. The price function for mid-sized cars is Q equals 20 minus y for values between 0 and 20. These are both in thousands of dollars, where x and y are respectively the numbers of compact and mid-sized cars per hour. If the company's cost function is C of xy of 15x plus 16y minus 2xy plus $5,000, find how many of each car should be produced and the prices that should be charged in order to maximize profit. Also, find the maximum profit. So, I have my cost function in place. I know my revenue for product A is going to be x times 17 minus 2x. And I know that my revenue for product B is going to be y times 20 minus y. Again, quantity times price. Quantity times price. So now when I put this into a profit function, I get this, and now I'm going to simplify it. And when I simplify it, I get the profit function to be 17x minus 2x squared plus 20y minus y squared minus 15x minus 16y plus 2xy minus 5. And they're putting it into a standard form here because, well, one, there's some like terms like these two can be combined. These two can be combined. There's no other constants. So we simplify a bit further, and we end up with this being our profit function: negative 2x squared minus y squared plus 2xy plus 2x plus 4y minus 5. Especially with the xy term in there, we can't really separate this. We can't really resort to doing single variable versions of this, so we are kind of stuck doing a multiple variable version. So we're going to find the partial derivative of the profit function with respect to x and with respect to y. And they just kind of did it here. Again, by this point, they're hoping that you know how to carry that through. And what they chose to do is, because of the fact that, rearranging this bottom one here to 2x minus 2y plus 4, if I add the equations as they are, these automatically cancel, and I'm ready to solve this equation for x. So I get negative 2x plus 6 equals 0, which negative 2x would equal negative 6, which means x would equal 3. And if x equals 3, I can substitute x equals 3 into either one of the two original equations and figure out what y would have to be. In this case, y would have to be 5. So I do have this ordered pair, this critical point of 3, 5. Now, what is it? Now, we're hoping it's a maximum. So we're going to do a d-test to see, first of all, if it is a maximum. And then, once we know it's a maximum, we can figure out what the maximum value is. So I'm going to do the second partial derivative with respect to x, the partial derivative with respect to x, and then respect to y, and then we're going to do the second partial derivative with respect to y. So from these two partial derivatives we established beforehand, pxx is negative 4, pxy is 2, pyy is negative 2. No, there's no variables involved, so at 3, 5, it's going to be the same thing as any other place. This is just 3, 5 is what make the first two original partial derivatives equal to 0. So when I plug that value in, I get positive 4. Since this is greater than 0, it is a relative. It is an extreme value. Now, as far as the minimum or maximum, when I look at this value right here, it is negative. And if that's negative, well, d is positive. That's going to tell me that I have a relative maximum. So I do know it is maximized when x is 3 and y is 5, which means that the maximum value is going to be, they find the prices and the quantities and things. It's just to basically plug in the whole thing to get your profit. And you plug all that in, you get about $8,000. I don't know why they show this part here. Because, you could kind of just do that by plugging the 3 and the 5 in their respective spots in the profit function, because you already kind of took care of all this stuff here by making a profit function. So the profit is maximized when the company produces 3 compacts per hour, selling them for $11,000 each. Oh, that's why. They wanted to figure out what the prices were. And 5 mid-sized cars per hour, selling them at $15,000 each. The maximum profit would be $8,000 per hour. So sometimes they do ask you some questions that are more involved, and ask you to find out a lot of detail about it. So, keep that in mind as you do them, because sometimes you'll be asked to provide that information as you go through it. So, kind of going back, that's why, again, when they went to this previous one, they figured out what the prices were. Because we already kind of knew what the quantities were going to be. We found x and y. So now they go into like monopolies and duopolies, and and they do give you like one question in the textbook that kind of has you like evaluate and study the results of it. Tell you with all honesty, I'm not even sure if that's one that's been assigned to you to do. Out of the list that you have in your schedule. It's worth a look at, but if you want to have a look and see how they interpret The effects of a monopoly versus a duopoly versus, having three competitors in the market or two or three suppliers or four suppliers. You know, the whole premise behind it is the more suppliers you have, the better it is for the economy in general, not just having one person or one company in charge of being the sole supply of a particular, item. So I'm not going to go into that too much. They show the entire breakdown, but this is all in your textbook. But even for all the monopoly and duopoly talk here, let's have you do a similar exercise. A company manufactures two products. The price function of product A is P sub A equaling 16 minus X, for X being between 0 and 16. So X, of course, is the number of units of product A. The product B is P sub B equaling 19 minus 0.5 Y, for Y being between 0 and 38. Both of these price functions are in thousands of dollars. The cost function is C of xy equaling 10x plus 12y minus xy plus 6, $1,000. They want you to find the quantities and prices that maximize the profit and also tell me what the maximum profit is. So answer this question and using all the work and fill in the blanks in this statement to answer the question completely. Well, the first thing I have to do to answer this question is I do have to figure out what the profit function is going to be. So I'm going to make the profit function. Well, the first thing I'm going to do is I'm going to have the revenue I get from product A. So that's going to be basically X times P of A, where I'm doing the quantity times the price, plus Y times P sub B, and I'm going to subtract away the cost function, C of X, comma Y. So that's going to be X times 16 minus X plus Y times 19 minus 0.5 Y minus this whole cost function. So I'll simplify this a bit. I get 16x minus x squared plus 19y minus 0.5 y squared minus 10x minus 12y plus xy minus 6. I do have a couple of like terms to combine, but I'm going to kind of put it in order as well. So negative x squared minus 0.5 y squared plus xy. So that takes care of this one, and this one. 16x minus 10x is a positive 6x, so plus 6x, which takes care of these two. 19y minus 12y becomes a plus 7y, which takes care of these two. And, oh, darn. And a minus 6. So that is my profit function in terms of x and y. So now the next stage is I got to figure out the partial derivative with respect to x and the partial derivative with respect to y. So the partial derivative with respect to x is going to be a negative 2x plus y plus 6. And I'm going to set that equal to 0. The partial derivative with respect to y is going to give me a negative y plus x plus 7 equaling 0. If I do some rearranging of these two, I have negative 2x plus y plus 6 equaling 0. I have x minus y plus 7 equaling 0. If I add these equations together as is, I get negative x, the y's cancel, plus 13 equaling 0, which means that x has to be 13. Y, going back to one of the original equations here, I'm going to choose this one here. If I have x being 13, I'm going to have negative 26 plus y plus 6 equaling 0, which means I'm going to have y minus 20 equaling 0, which means y would have to equal 20. So I do have a critical point at 1320. Now, as a side note, didn't leave myself a whole heck of a lot of room here, but still none the kid. I'm going to do a test to make sure that this is in fact a maximum. So I am going to do the D test. So I'm going to figure out what P of XX is, P of XY, and P of YY. This becomes negative 2. This becomes 1. This becomes negative 1. So the D test is going to be negative 2 times 1 take that back. XY. No, that's be YY. Negative 1 minus 1 squared, which does equal 1, so it's greater than 0, so it is a relative minimum or maximum, and since this is less than 0, I do have a relative max. So it's always good to kind of do that to make sure that you are calculating things right. If you find a critical point, great, but you want to make sure it's the right type of critical point and make sure you didn't make any mistakes with your variables. So I do know that 13 and 20, 13 of product A, 20 of product B is what I want. But I got to figure out the other parts of this. So, the price for A is 16 minus 13. So that's $3,000. The price of B is 19 minus 0.5 times 20, which would be $9,000. As far as the profit goes, I'm going to come back to this function here and do negative 13 squared minus 0.5 20 squared plus 13 times 20 plus 6 times 13 plus 7 times 20 minus 6. And when I do that, I get 103, which indicates $103,000. So I don't know what these things are. They're, if they're selling for $3,000 and $9,000 a piece, they should be kind of up there in price. But there you have it. So I would need to sell 13 units of product A at $3,000 a piece, 19 or 20 units at $9,000 a piece of product B to earn a maximum profit of $103,000. But you don't actually have to do this optimization just for maximum profit. So for the last example I'm going to have you do, the number of office workers near a beach resort who call in sick on a warm summer day is given by the function f of xy equaling xy minus x squared minus y squared plus 110x plus 50y minus 5200, where x is the air temperature between 70 and 100 degrees, and y is the water temperature between 60 and 80 degrees. Find the air and water temperatures that maximizes the number of absences. So take a moment to compute this out, and we'll go over it momentarily. Okay, so we first define a critical point. I'm going to do a test to see what kind of critical point it is to make sure it is going to produce a maximum. And then I'm going to, figure out what the air and water temperatures have to be to maximize the number of absences. The question you were asked did ask for what the number of absences were, which is fine. But this question here just said find the air and water temperatures. But with that information, you can find everything else needed. So the first thing I'm going to do is I'm going to find the partial derivatives with respect to x and respect to y. So I'm going to do f sub x and f sub y. So taking the function as it's written, xy, the derivative of that with respect to x is going to be y. The derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is 0 because y squared would be considered a constant. The plus 110x would become a 110. And the plus 50y and minus 5200 would both be considered constants, so they would become 0. And I will be setting this equal to 0 because the critical point is going to be, at a place where that's going to happen. The partial derivative with respect to y is going to give me x. The xy is going to become x. The minus x squared is going to become a 0 in this case. So I'm going to have the next term, the minus y squared is going to become a minus 2y. The plus 110x is a constant, so that's going to become a 0. The derivative of positive 50y is just going to be a plus 50. And the minus 5200 is also a constant, so it's going to be considered 0. And I'm going to set that equal to 0. So again, I'm going to set up my functions here. I have a negative 2x plus y plus 110 equaling 0. I have x minus 2y plus 50 equaling 0. It's really up to you which you want to eliminate, because there's not one that just automatically cancels out at this point. I'm going to opt to multiply the bottom equation by 2, and that's going to make the x's cancel out. So this will become negative 2 at the top, nothing happens, so everything stays the same. The bottom, I'm going to have 2x minus 4y. Make sure to multiply everything by 2. Plus 100 equals 0. These cancel. I am left with negative 3y. Is it negative 3y? Yeah, plus 210 equals 0. So negative 3y would equal negative 210. Yeah. Which means y would equal 70. If y equals 70, I go back to one of the originals. I'm just going to come back to this equation here. X minus 2 times 70 is 140. Plus 50 would equal 0, which means x minus 90 would equal 0. So x would equal 90. So we have a critical point that we've discovered. The air temperature being 90 and the water temperature being 70. Now, is that going to maximize things? So let's have a look at that. So I'm going to look at fxx, fxy, and fyy. F sub xx is going to be -2. F sub xy is going to be 1. F sub yy is going to be -2. So when I calculate the d value, I get -2 times -2 minus 1 squared. That gives me 3, which is greater than 0. So it's going to be a critical point. It's going to be a relative max or min. And because this is less than 0, I know it's a relative max. So it is going to be a maximum. So now I can make a final statement for this. And going along with the way the question was phrased and the blanks you had to fill in, based on this model, when the air temperature is 90 degrees and the water temperature is 70 degrees, f of xy reaches a maximum of 1500. Therefore, the company will have its highest absenteeism of 1500 on that day. So that is all I have for now. If you have any further questions, please be sure to bring them up in class. Until I see you there, have a good day.